it shouldn't come to a surprise that one of the oldest topics in mathematics has to do with dealing with accounting numbers. So the numbers we use to count things, as their name indicates. So 1, 2, 10, 100, 69, all those numbers that we use to count books, oranges, I don't know, the number of days that we went to the doctor or something like that. Now, they may seem like pretty boring numbers, and in fact, they're not numbers that we study in high school because they just seem too simple. We spend time on fractions and on integrals and on all those hard things. But in fact, number theory is one of the deepest and most complex topics in mathematics, and it still has a lot of implications nowadays, and a lot of applications. So what we're going to study is elementary number theory, which in some sense are the most basic tools that you need for number theory and for studying integer and natural numbers. So we're not going to get into the really complex stuff, which even I don't understand, of analytical number theory and all that crap. We're going to stick to elementary number theory. So I've put elementary in brackets here because though this subject is approachable, it's not an easy topic. This is going to be a proof intensive. There's going to be a lot of proofs in this series, but don't let that discourage you. It's the perfect topic to be introduced to proofs, to be introduced to mathematical formalism, and it's truly a fascinating topic. So, elementary number theory. It's the study of the elementary counting numbers, as I said. Very old field of study in mathematics, and still studied today. Some of the oldest, most famous, and most difficult conjectures in mathematics. So maybe you've heard of the Goldbach conjecture or the twin primes conjecture. Now these conjectures are easy to read and understand. It's not like a conjecture in topology where you need to have spent a lot of time trying to understand just the terminology of what's being used in the conjecture. But these are problems that have been standing for more than 200 years but still haven't been solved with the most incredible mathematical tools we've been able to come up with. So they're definitely not simple problems, but we may deceptively look so. Now, elementary number theory does have some direct applications. In fact, if you use computers, you're using them every day. Encryption, namely RSA encryption, uses number theory directly, and we're going to talk about RSA encryption in this series later on because we can actually approach that with elementary number theory tools. Now, nowadays there are more sophisticated encryption algorithms, but those are more complicated to understand, so we're not going to talk about those. So if you've heard of Gauss, apparently he said that mathematics is the queen of the sciences and number theory is the queen of mathematics. I'm not going to say any sources for that because I don't know if it's true. So what you see down here is set notation. These are letters that indicate sets. Sets meaning a collection of objects. And so we're going to study those first two letters you see down there, which are the natural numbers with n and the integers with z. Sometimes they're also indicated with I, but we're going to use z because that's more common. So the natural numbers are the basic counting numbers, 0, 1, 2, 3, 4, all that. While the integers are those numbers with negation. Negation meaning we also have -1, -2, -3. And just allowing negation allows us to conveniently define more arithmetic and just do more stuff. Now we're not really going to get to the rationals because there's a big jump from the integer to the rationals, and we're definitely not going to get to the reals because there's an even bigger jump from the rational to the real numbers to get, and that's just a different field of study where we get to real analysis. And then from the reals to the complex numbers, that's complex analysis, and that's completely off bounds. So, the counting numbers, the naturals. What are they? So at first, we may want to say the natural numbers is the set 0, 1, 2, 3. We can write ... to infinitely say that we have 4, 5, 6, 7, all that. That's just notation. But as I said, this is a course in formalism, and we want to be formal about this. We want to be rigorous. And so the problem is, how are we going to introduce the natural numbers, which is an infinite set, but only use finitely many logical statements? This may seem like a strange question to ask, and to understand why that is a valid question, we need to understand what we mean by mathematical axioms. So in science, when we do science, the questions we ask is, what are the fundamental laws that govern reality, if there are any, and how can we deduce those laws from observations? So science is, by definition, an inductive process where we observe things many times, and that strengthens our belief that those things are true, and that we can deduce some fundamental laws about the universe from those observations. Now, in mathematics, we don't like that, and in fact, we do completely the opposite. We like to be a lot more factual, but that's also because we can afford to be a lot more factual. In some sense, mathematics is a lot easier because in mathematics what we do is we're given a set of fundamental laws, and in fact most of the time we invent that set of fundamental laws. And from that set of fundamental laws we explore the abstract reality that is necessarily generated by them. And so those fundamental laws are called mathematical axioms. And so in some sense there is no mathematical fact that we discover for a particular system of fundamental laws, because instead it's just a sort of necessary logical byproduct of those foundations. And the more discovery-like part of math is just figuring out the least obvious of those byproducts, and obviously also the most useful one, because we could go far and all and make some proofs about some very, very abstract things, but they probably wouldn't be very useful and no one would really care most of the time, except for mathematicians. And so as I said, the foundations of a particular system are called its axioms. So now we want to ask the question, what are the foundations of the natural numbers? What are the axioms for the natural numbers? And so one set of axioms for implicitly generating the natural numbers, and that's what I was saying, we could consider an infinite set of axioms where, maybe the first axiom is saying 0 is a natural number, then we have the second axiom that says 1 is a natural number, and a third axiom that says 3 is a natural number. But we're not infinite beings, and we can't, be saying axioms for an infinite amount of time. We want to stay concise, we want to be able to write the axioms down on paper, and from there to get the infinite set that is the natural numbers. And so to do that, we're going to start from the Peano axioms. I don't know if I pronounced that correctly. So the Peano axioms start by naming one particular natural number, and then we generate all the other natural numbers by using a single operator, which is called the successor function. So we'll talk more about that here. So the first Peano axiom, and maybe the most important one, is to say that 0 is a natural number. As I said before, the Peano axioms start by naming one particular natural number, and if we didn't do this, then you'll see from the next axioms that the natural numbers would just be an empty set, and we'd have nothing, no numbers, and we'd be done. Elementary number theory would be over. So we need this axiom here. 0 is a natural number. That's the most fundamental thing. Now, in some treatments, you'll see that the Peano axioms instead say that 1 is a natural number. For the purpose of this series, the natural numbers are going to include 0 as well. And that's just because it's convenient to use 0 as the symbol for an additive inverse, and it's convenient to have the additive inverse in the natural numbers. Not the additive inverse, I mean the additive identity. And so we'll include 0 as a natural number in here. But in Peano's original treatments, the first natural number was 1, not 0. So then from there, we need to use the successor function, or operator s. So the function s, or the operator s, is a so-called unary operator, which differs from a binary or a ternary operator because it acts on one object. That's what an operator or a function does. It acts on a certain amount of objects and it produces some new object or some new collection of objects. In our case, it's basically the functions we study in high school. Like fx equals x squared. We take the object x and we output the object x squared. That's a unary operator or a unary function. In our case, it's not going to have that kind of explicit formulation because that requires some other stuff. And it's going to be a lot more implicit, and we'll see how we define the successor function s. So for now, just tell yourself that there is somewhere floating in space a successor function s, and we don't really know what it does except that it takes one input and it returns one output. So the second axiom says that for every natural number n, Sn representing the output of applying the operator s to n, is also a natural number. So let's see what that means. We have the first axiom, which states that 0 is a natural number, and now we've got the second axiom, which states that for every natural number n, Sn is a natural number. So if 0 is a natural number, then by this second axiom, S of 0 is also a natural number, right? So we've already got a set with two elements, 0 and S of 0. Or so we may think. If you know anything about sets, you'll know that sets do not care about repetition of elements. I can only have 0 once in the natural numbers. I can't have 0 a bunch of times. And I don't have any guarantee here that s of 0 is not 0 itself. So we're going to have to guarantee that if we want to get further into the natural numbers. Otherwise, we start with 0, we create s of 0, but that ends up being 0, and then we're just done. And we can't do anything more. So that may seem like enough of restriction to get the rest of the natural numbers going, but we're also going to have to consider a little bit more, because let's imagine that s of 0 is not equal to 0, right? So then by these two axioms, right, I've got 0 as a natural number, I've got s of 0 as a natural number, and now by this second axiom again, I've got s of 0 is also going to be a natural number. But we have no guarantee that s of 0 is not 0, and we also have no guarantee that s of 0 is not s of 0. If s of 0 is s of 0, then we're just going to be looping back on our second natural number, and we're not going to be generating anything more. So we're going to need to deal with that, and this may seem like a bit of a complicated topic, because how are we going to deal with every possible combination? How are we going to deal with, say, applying s 20 times to 0 and saying that can't be 0, that can't be applying s 1 time, that can't be applying s 2 times, 3 times, 4 times, all the way up to 19 times, and we have to deal with that for any successive applications, or s. And we still want to do this with finitely many axioms. So the first thing we're going to want to notice is that there's only really two types of natural numbers. There's 0, and there's the rest, which has come from the successor function. And we're going to see that we can encapsulate not repeating those numbers in exactly two axioms for those two cases, which I laid out down here. So the first one is that there's no natural number n for which s of n is equal to 0. That means the successor function can never be equal to 0. So that already deals with the case that s of 0 is not equal to 0. That already guarantees that we have at least two elements in the natural numbers, 0 and s of 0, that are distinct. However, now I can apply s to s of 0 and get s of 0. Now by axiom 3, that's not going to be 0, so that's cool. But how do I know that's not equal to s of 0? And that's where I bring in my fourth axiom, which makes s as an injection. So what is an injection? Injection is a function that is 1 to 1. That means that if I look at any output number, there's only a single input number that corresponds to it. It's 1, that's why we say it's 1 to 1. If you look at the function f of x equals x squared, that is not an injection, because if I look, for example, at 1, well, 1 squared is 1, but if I look at minus 1 squared is also 1. But I only want one input to give the output 1. I could do similarly without being as confusing as using the number 1. I could do the same for 2 to 4 and minus 2 to 4, but that's just more general. But if you look at the function, for example, fx equals x, that is an injection, because I can invert that function. And it actually turns out that a function being an injection is necessary for a function to be invertible. So the way we state that s is an injection is that we say that two numbers m and n are equal if and only if those numbers under that function are also equal. Now, note that I've been using equality here, but we haven't actually defined what equality means. We want to be rigorous here. In the original Peano axioms, there are axioms for defining equality, but in modern treatments nowadays, equality is also sort of a part of first-order logic, and we don't really need to include it into our axioms. And I'm also just going to assume that you know what it means for numbers to be equal, so we're going to loosely just include equality as being something that's pre-established and we know what it means. So that might not be super rigorous, but that's what we're going to do. So anyways, looking back, m equals n if and only if sm equals sn. Now that if and only if, that's a sentence you're going to see a lot, and sometimes it's easier to think of that sentence as meaning that the two statements here, m equals n and sm equals sn, are equivalent statements. That means that they mean exactly the same thing. So if I start with the statement s of m equals s of n, then I know that m equals n. But if I start with the statement m equals n, then I also know that s of m is equal to s of n. So now let's look at our problem again. So we start with 0. That's the first natural number. Then we create s of 0, which we know is distinct to 0, so that's our second natural number. And now we create s of 0. Now we know that's not 0 by the third axiom. But now let us assume that it is equal to s of 0, so that, we get a problem and the natural numbers stop there. Well, if s of 0 is equal to s of 0, then by this fourth axiom, s of 0 is equal to 0. But by the third axiom, that's not possible. And so you see how this fourth axiom here allows us to successively remove applications of the successor function until we're only left with 0. And then using the third axiom, we can show that using this sort of infinite descent, well, we could never have a situation in the first place. And that actually takes care of all of the possibilities of, say, applying s 100 times. Well, that can't be equal to applying s 99 times or 98 times. And so that axiom is going to be enough for that. And so now it looks like we're done with the natural numbers. Those four axioms seem to infinitely generate 0, 1, 2, 3. Well, I'm not going to say 1, 2, 3. In fact, this only guarantees that we have 0, s of 0, s of s of 0, s of s of s, s of s of s of s of 0, and so we think we're done, but we're still missing one tiny little thing, and in fact, it's not that tiny at all. It's very important. It's to make sure that these are the only natural numbers. Because what's stopping me from defining some number k, right? And saying, hey, that guy's a natural number, and then sk is a natural number, and then s of k is a natural number, and, I can just add a bunch more without really saying what k is. Because keep in mind, in your head, you might think that the successor is equivalent to adding 1, but you've got to get away from that. The successor is really the first operation that says that. So if I used the symbol -1 and included it to the natural numbers, then I don't have a guarantee that s of -1 is not equal to 0. So it could still be a natural number. So how are we going to get rid of that? Well, we have to introduce one final axiom, which is the axiom of mathematical induction. It's a bit of a confusing axiom at first, but it's very important, and we're going to be using it a lot in proofs. So if P is a set such that 0 is in P, and such that for every n, which is in this bold n here, that means the natural numbers. So for every n belongs to the natural numbers, so for every natural number, then n belonging to P implies that s of n also belongs to P. Then we know that the natural numbers are a subset of P. So this may all seem very confusing. Let's try to think about this more concretely. So we have a set, right? P. We don't really know what that set is. And we know that 0 is in P, and we know that if there is a natural number in P, then the successor of that natural number is also in P. Now keep in mind that the successor of a natural number is also a natural number. So intuitively, you may think, well, that means that every natural number is in P. And in some sense, you'd be right, but it's hard to really just intuitively say that because we're talking about an infinite process. We have infinitely many natural numbers and we keep adding them. And we need to include an axiom that really explicitly formulates that intuitiveness about that infinite process. So that's why we say that the natural numbers are a subset of P. And so why does that guarantee that the numbers we generated are the only natural numbers? Well, consider just the numbers that we generated, so 0, s of 0, s of s of 0, and then just applying s a bunch of times to 0. Well, now let's say that set is P, right? So we know that 0 is in P, and we know that n being in P implies that s of n is in P, because that's just one of the axioms of natural numbers. So then by this axiom here, the natural numbers are a subset of 0, s of 0, s of s of 0, and that infinite set there. So if anything, the natural numbers need to be at least that set or smaller. But they can't be smaller because, as we said, for every natural number, we imply that s of n is also a natural number. So that restricts our size to exactly those numbers and not more. Now, another way to formulate induction, which will be very useful later for proofs, is to write it this way, which is if P of n is a property on n, so that P of 0 is true, so that means that the number 0 has that property, and such that for every n that is a natural number, P of n implies, well, P of n being true implies that P of s of n is true. Then P of n is true for all natural numbers. So what that means is that I can think of some property, right? And we can show that 0 has that property. And then we assume that some natural number, but any natural number has that property, right? And the fact that that natural number has that property must require that the next natural number also has that property. And combining that with the fact that 0 has that property creates a domino effect that applies the property to all the natural numbers. Because we know that 0 has that property, right? And because for every n a natural number, p of n being true implies that p of Sn is true, then p of 0 being true must imply that p of S of 0 is true, right? So the next natural number after 0 also has that property. But then applying that again, the next natural number after that also has that property, and then the next one after that, and after that, and after that. And so that applies the property to all of the natural numbers. And this is actually the same statement as for 5, where when we're looking at that set P, when we say if P is a set, you can simply think of P as being the set of numbers that have the property that we're using here, and then that becomes exactly the same statement. So what do the natural numbers actually look like? Well, we have 0, and 0 with our axioms implies that S of 0 is a natural number, and that implies that S of S of 0 is a natural number, and so on. So the natural numbers are actually this set here with the successor function. And we don't actually see 1, 2, 3, 4, all of that. Those are just completely unnecessary and arbitrary symbols. Now, unnecessary is not true. We're going to use those symbols a lot because writing S of 0 a bunch of times is just completely inconvenient. But note that I can really use whatever symbols I want. I could say 0, A, B, D, orange, apple, and if I want that to be the symbol for the number 4, then sure. So, before we continue, I want to introduce something that's again related to the axiom of induction, called the well-ordering principle. And the well-ordering principle is actually equivalent to the axiom of induction. But it does not at all sound like the axiom of induction, and it's an incredibly important tool to have when we want to do proofs. And it may seem very intuitive and useless to say, but it's something that we've got to prove. So, what the well-ordering principle says is that every non-empty subset of the natural numbers, so that means if I take any collection of natural numbers, right, S that is a subset of n, has a minimal element. That means that it has a smallest element, right? So, for example, if I take the subset of natural numbers 3, 7, 8, the smallest element of that is 3. And so what this theorem is guaranteeing is that there always will be a minimal element. Now, note that this wouldn't work for the integers, right? The integers also include negative numbers. And a non-empty subset of negative integers could, for example, be every number that's smaller than -1. But then we don't have the smallest number, right? We'd have a maximal element, but not a minimal element. But we wouldn't be able either to guarantee a maximal element with integers because we could just take all of the integers, that's a subset of integers, and there's no maximal or minimal elements. The fact that the naturals start at 0 and then go off infinitely to the right, it kind of guarantees that minimality. So that's the intuition for it, but let's actually prove it. And we're going to prove it using induction. So, let's let S be a subset of the natural numbers with no minimal element. So this here is a common proof technique called proof by contradiction. We assume that the statement we're trying to prove is false. And then we show that using facts that we know to be true, that's just not possible. Like, it would contradict one of the facts that we already know to be true, so that means that it must be true as well. So let's see. Clearly, 0 is not an element of S, right? Because if 0 is an element of S, then it would be a minimal element of S, because there is no natural number that's smaller than 0. Oh, by the way, smaller than, we haven't defined the relations smaller than or bigger than. I just assume that you know what they mean. It is a part of the axioms of Peano arithmetic to define the smaller than and bigger than relationships, but I just didn't include it here to not clutter things up. So, if 0 is not an element of S, then 0 is definitely an element of S naught. What that little tick means means that everything that's not in S, right? It's the set of all elements that aren't in S. And in this case, it's the set of all natural numbers that aren't in S, right? Now, suppose that we have some n that's a natural number, right? Suppose that every positive integer that is smaller than n, so every natural number that is smaller than n, is also in S naught. Well, if n plus 1 was in S, then it would be the smallest element of S, right? Because every integer that's smaller than n is not in S. But that's not possible, sorry, because S has no minimal element. That's what we said at the beginning. So n plus 1 has to be in S naught. But by the axiom of induction, that means that S naught is a subset of the natural numbers. Now, why does it mean that, right? Because, let's see, we have that 0 is in S naught. And we have that n plus 1, well, n being in S naught implies that n plus 1 is in S naught. So that means that the natural numbers are a subset of S naught. I wrote that the wrong way around. Now, that's a contradiction, because if the natural numbers are a subset of S naught, and we know that S naught is a subset of the natural numbers, then that means that the natural numbers is equal to S naught. But then that would mean that S is which is a subset of the natural numbers, would be empty. So therefore, there is no non-empty subset S of the natural numbers with no minimal element. And so the well-ordering principle is proven in that sense. Now we can also prove induction using the well-ordering principle. We could have formulated natural numbers with the well-ordering principle as one of the axioms instead of induction. And so that's what we're going to do here, just to show that those two statements are actually equivalent. So let's start by bringing in what induction talks about. We're going to use the property interpretation. So suppose P is a property on the natural numbers such that P of 0 is true and that P of n implies that P of S of n is true. So that was just part of induction, and we just have to introduce it in here. Let's see what we can do with that. So let's let K be the set of natural numbers K such that P of K is false. Now suppose K is non-empty. Then because of a well-ordering principle, it has a least element n. So why are we supposing here that K is non-empty? This is going to be a proof by contradiction as well, right? If you can see it coming. Because we know induction is we're doing a proof of induction, so I'm telling you that induction is true when we start with a well-ordering principle. So we're going to have to show that K here is actually empty, because all of the natural numbers are true because of that property we have at the top here. So we're going to show that K is actually empty. We're going to show that this supposition that K is non-empty leads to a contradiction. So suppose K is non-empty, it has at least element m by the well-ordering principle. So since P of 0 is true, 0 can't be in K, because that's just the definition of K. And so m is not equal to 0. So that means that m minus 1 is a natural number, because if m was equal to 0, then m minus 1, that's not a natural number anymore. We haven't actually defined the arithmetic of m minus 1. We're going to do that after, but that's fine. Let's just say what subtraction is. So m minus 1 then is a natural number, which is also not in K, because m is supposed to be the minimal element of K, right? So by definition, we therefore have that P of m minus 1 is true. However, by the properties of P, the fact that P of m minus 1 is true implies that P of m is true. So m can't be in K. I wrote that wrong here. That's a contradiction, because if m is not in K, then that's a contradiction to the fact that it's its least element. So that means that K has to be empty, and P of n is true for all the natural numbers. Because if P of K is empty, then if K is empty, then P of K is true for all the natural numbers. So let's actually define some useful arithmetic by using the successor function. So there's addition, obviously. And we're going to define it as such by saying that a plus 0 equals a, and that a plus successor of b is equal to the successor of a plus b. So let's see that with an example. A plus 3, right? That's going to be a plus the successor of 2, because we know that 3 is the successor of 2. So that's going to be equal to the successor of a plus 2 by this definition here. That's equal to the successor of a plus the successor of 1 by applying that again. So you see we're just consecutively applying the successor backwards to the symbols that we have for them. And so that's the successor of a plus 1. And then once again, we apply the successor to 1 to get that that's the successor of 0. And we move things around to get that that's the successor of the successor of the successor of a plus 0, which is the successor of the successor of the successor of a. So it's applying the successor 3 times to a, that's a plus 3. So that makes sense. So what about multiplication? Multiplication, we say that a times 0 equals 0, and we say that a times s of b equals a plus a times b. So let's see. Note what happens when we do a times s of 0. So a times s of 0, that's equal to a plus a times 0, which equals a plus 0, right? Because a times 0 equals 0. So that's equal to a. So that shows that s of 0 is the multiplicative identity, at least on the right. Because in our definition here, we don't actually have multiplication as being commutative. Commutative means that doing a times b is the same as doing b times a. But nowhere do we guarantee that here. Now, you can prove that multiplication is commutative just from this definition. And you can also prove that it's distributive, which means that a times b plus c is equal to a times b plus b times c. So it distributes over addition. We're not going to do these proofs though, because that's just going to clutter things up, and I expect that you are already familiar with multiplication. What about division though? We have addition, and we have multiplication. And in fact, we can also, introduce subtraction by looking at the integers z, which also contain the additive inverses of the natural numbers. And so the additive inverse of n is just a number minus n, so that's n plus minus n equals 0. But introducing division would mean that we'd have to go from the integers to the rationals. But that's straying away from our study of accounting numbers, But we still want to do stuff with division. We don't want to completely get rid of division. And in fact, divisibility is one of the most important aspects of number theory. So we're going to have to think about it a little differently. For this video, for now, we're going to look at about a lot more detail in the next video, but for this video, we're only going to look at proper division. So proper division, we now define as this relation that looks like a pipe, and we say that A divides B, that's what the little pipe means, if and only if, the double arrow means if and only if, B is equal to AK for A, B, and K belong to the integers. So what that means is that A is a divisor of B, but B exactly divides B. For example, I take 10, right? And I know that 2 divides 10 because 2 times 5 is equal to 10. So here are some properties of divisibility for, let's take D, N, and M all belong to the integers. So the first obvious one, well, maybe not so obvious one, is that D divides 0. Because note that for any integer D, I can just multiply it by 0 and I get 0. So all of the integers are actually divisors of 0. Next is that if 0 divides n, that means that n is equal to 0. Because once again, 0 times anything is equal to 0. So that it can only divide a number n if n itself is equal to 0 as well. Next is that 1 divides n, because I can always do 1 times n, that's equal to n. That's also pretty obvious. Then n dividing 1 means that n is equal to 1 or n is equal to minus 1. That's kind of a similar logic to for 2, except that we know this because 1 is a multiplicative identity, as we saw earlier. N divides itself. That's also quite obvious. It's called the reflexivity property. D dividing n and n dividing m implies that D divides m. That's called transitivity. Now that might seem a little less obvious. Let's look at an example, for example. We know that 2 divides 10, because 2 times 5 is equal to 10. And we know that 10 divides 20. So that must imply that 2 divides 20. And we could have seen that from the start, but in the more general case when we deal with variables, this is going to be quite a useful property. And I recommend that you try to prove it by using the definition that we have at the top there, b equals ak. Now, the multiplication property. D dividing n implies that AD divides AN, for A is an integer. I also recommend that you try to prove that. AD dividing AN and A not being equal to 0 implies that D divides N. That's a little, the A not equal to 0 parts, you do have to be careful about that, but in general we can cancel things for division. Just have to check that A is not equal to 0. So it's basically the inverse of that multiplication property. It kind of feels like division actually. Then this is probably one of the most important properties that we're going to be using as well, linearity, which is that if D divides N and D divides M, then D divides AN plus BM for any AB or integers. That's quite astonishing. If I take, for example, 3 divides 6 and 3 divides 9, right? Then I can take any linear combination of 6 and 9. So I can take 1,000,000 times 6 plus 64 times 9, and I know that 3 will divide those. And I recommend that you try and prove that as well. It's not a very hard proof. And then finally, if D and N are both positive, and D divides N, that means that D must be smaller than N. And that also seems pretty obvious. If 2 and 10 are bigger than 0, and I know that 2 divides 10, so that shows me that 2 is smaller than 10. Well, smaller or equal to. So as a homework exercise, I guess, you try to prove properties 6 to 10. You can also prove the other ones if you want, but I mean, they're just so obvious that it's not really useful. You may want to make use of the trichotomy property to make at least the last proof rigorous, which is that for two numbers a and b, either a is smaller than b, a is equal to b, or a is bigger than b. That's pretty obvious, but if you want to make the proofs rigorous, you will have to call it. And that's it for this video.